this keynote address by Professor Cathy Chin. So it's a great pleasure to introduce Cathy. Cathy Chin joined the PNL right after she received a master's degree and the BS degrees from University of Oklahoma from Daniel Rosasco's group. And I had a great honor working with Cathy for 5 years before she deserted us. I have to tell a story. From day one, Cathy joined the PNL. Everyone thought she had a PhD degree, and she actually worked like someone with a PhD degree. So that actually eventually led Cathy to determine to have a PhD degree from Professor Iriki's group at Berkeley. And in 2011, Cathy became faculty member in the Chemical Engineering and Applied Chemistry Department at the Toronto University. And she is a professor now, and also Canada Research Chair, and also the associate editor of Journal Catalysis. So Cathy, podium is yours.
Thank you so much for the invitation. And I would like to entertain you for something that we have been thinking about for the last few years or so. So hydrogen atoms on solid surface acquire different charges. For example, on transition metal surfaces, metal donated a free electron into the hydrogen, so it acquires slightly partial negative charge. If we look at hydrogen, reactive hydrogen or sulfide nitride and oxide surfaces, you have hydride and proton pair. And also when you go all the way to silica alumina due to the requirement of charge balancer, then we have an entire proton. To make this story more complex is that we immerse the solid surfaces on in the solvent. Then it is where the electrical double layer now happens, and we have here a net dipole orientation, net charge density, and all these together kind of shape the free energy landscape and control the reaction. So we have here hydrodeoxygenation that include a series of chemistry that saturate the aromatics, that reduce the polar carbonyl bond, and also cleave the strong carbon-oxygen bond. The idea here is something that we have think about on my group and also our collaborator, John Sabin Allen in the audience, Manos Mavakaki's group, and also collaborator in DuPont to understand or how to tantalize and change the charge of the hydrogen species, and how the hydrogen species participate in the reaction, and how could we change the reaction pathway, and how could we manipulate the reactivity. So here, this is not about single step. This is about a series of hydrogen attack sequence. A small hydrogen, each one needs to attack the oxygenate or the aromatic heat recycle. They are charged, and how do they interplay and give it the resulting reactivity. Let us start with here a simple cases of hydrogen on vapor transition metal surface, no proton or anything, simple thing. And let us use here a simple molecule to see how hydrogen activate and attack. It's kind of simple, it's two done steps. You have an OH bond formation, you have a CH bond formation, two steps, step 1 and 2 attack, and you get your alcohol product. Sounds simple and easy, but it is not that simple. Either you have a right foot forward, CH bond formation, or you have a left foot forward. This is not the same in the free energy landscape. Two hydrogen attack, and depend also on whether you have CH or CH bond formation, or the relative size of these peak in these two steps, we get different sequence. And for here, this is take here an aldehyde. The hydrogen and that go to either first step or second step on the surface that could be covered with different intermediates. We use CO to control this term, so this is constant, and evaluated exclusively the dependence of hydrogen. This is second, so second hydrogen attack is kinetically relevant for the hydrogenation of aldehyde on ruthenium surface in the vapor phase. Then we could use here isotopic labeling method to now map the free energy surfaces. We could have here a aldehyde and reacted with D-label atom to form here either 1D reactant, we put up that step. Overall hydrogenation is this part. We can also bring here a product in order to do the back exchange to understand the relative rate and interplay of the 3 different catalytic sequences. It is really not that simple with what I've drawn here. So I give you here the full consideration of the entire pathway of aldehyde and D2 reaction. We have alkoxy pathway CH1 formation before OH1 formation, hydroxy pathway OH1 formation before CH1 formation give the same 2D product. But we also have here some back exchange to make 1D reactant. We also have here 3D product because of this thing. Let us consider all these, measure all these D-label products, take here a product to do reverse exchange. What we have seen here is that second step are the slow step, hydride attack, and the hydrogenation reaction are much slower than the reverse part of that part. So this is larger, higher than that peak. So this is kinetically relevant, confirmed also by the reverse step having the product. This one is slow. The chemistry changes when we go from the vapor ruthenium interface to put here a ruthenium sulfide surface. Now we have hydride proton pair, no solvent. We activate the hydrogen hydrolytically, and these are the changes. Alkoxy pathway is still the pathway, but then the second step now becomes much faster. The first step is now slower. This is a change in the catalytic depth. So the first step now is the kinetically relevant as we use NMR to identify all the product, as well as using DFT to confirm that because we have the proton, this one proton attack and forming the OH bond is fast. Now the CH bond formation becomes the rate limiting step. Okay, now let us go on to go to this to go to the point by having now water, a slow amount, 1%, 2%, 3%, and see how all the rate changes. As we increase the water chemical potential, dropping this one drop at a time, these rate changes, hydrogenation rate increase, actually promoted. The reverse reaction rate, this one used to be fast, but getting slower and slower as we add water. So this part are changing, and this part remain essentially similar. This indicates that this step is being promoted, that one is changing, so water has now altered the free energy landscape of this reaction. And we do so for a series of aldehyde and ketone. These are the turnover rate as a function of different carbon atoms. But more importantly, when we immerse this reaction all the way into liquid water, a new situation happens. The new situation happens here, give us a water-ruthenium interface, a different reverse trend. And this part is related to the incipient formation of an interfacial proton. Hydrogen now donated electron into the matter D band and ready to do the chemistry. First step is proton transfer, attacking the oxygen. Second step is now the CH bond formation that complete here the catalytic cycle of 2 steps. We have changed the mechanism. Alkoxy pathway all the way to protic solvent, a proton transfer pathway. We have changed the reactivity trend for the entire series of aldehyde and ketone species. And let us now dwell a little bit more to understand how the solvent could form the proton and could change and shape the reaction free energy landscape. In water, we have this part, absorption, proton attack forming a charged intermediate OH1 formation, and then followed by the CH bond formation. This part is largely unaffected by solvent or the identity of the reactant, and that part here is captured with the equilibrium constant in the effective rate constant. To explain the effects of various things, solvent, matter identity, reactant identity, onto this effective rate constant, let us break down and analyze this equilibrium constant for that stage to that state. equilibrium constant is easier. Steady function. Let us construct here thermochemical cycle. Let's take it from the solvent water route all the way to here, going to desolation of the reactant and ionization of the hydrogen, and here a check of the proton in the gas phase at the proton affinity. Take this hydrogen electron, put that into the electron band, and the charged intermediate move it back into the solvent at the solvation entropy. And here we could capture effect of reactant identity at the proton affinity, this part, metal identity, and effect of solvent on the equilibrium constant. Reorganize all the reaction rate, plot it at the first order rate constant. Turnover rate is a function of proton affinity as captured here for this part of the thermochemical cycle. About solvent. We need the solvent here to stabilize here a charged intermediate. As a result of that, the solvent will stabilize the intermediate much more than that intermediate, so there is effect of summation. As we capture by this step, here the effective rate constant is a strong function in the log scale of the inverse of dielectric permittivity of the solvent for the entire series of alcohol, including the water here, as well as dioxide water solvent mixture, they fall into the thread, strongly related to the ability of the solvent to stabilize the charged intermediate. And to summarize this part, as the interfacial proton is formed in the presence of the protic solvent at the water and ruthenium interface, the free energy landscape looks like this. Proton transfer, fast quasi-equilibrated. Second part is the rate limiting step. And go here, the hydride proton or hydrogen atom in the vapor ruthenium surfaces. We have alkoxy pathway, kinetically relevant steps are different. OH bond formation for the hydrogen atom attached, but CH bond formation on the hydride proton pair chemistry that change. It is the relative dance step that the hydrogen, because of their different charge and because of the solvent that is able to stabilize the intermediate, that has multiple effects that change the relative size of the two steps. Okay, let us now, that is why we come to the point that on ruthenium sulfide species, the reaction rate of the aldehyde is related to hydride affinity, and the rate on the solvent species is related to the proton affinity that I have shown before. That is captured into the Born-Haber thermochemical cycle, and I know I haven't explained this metal identity. So in order to understand and capture the effect of the metal identity, how metal promote on the transition metal survey, take the electron from the hydrogen forming interfacial proton and to the chemistry, let us now give a probe reaction that clearly understand and capture this part. We go on with the phenol deuteration reaction. The reason is that this is a well-established homogeneous reaction that can be done with the hydronium ion in the free solution, no catalyst yet. What happened here is that the hydronium ion will undergo electrophilic attack on the specific position of the phenol in the auto and para position because the OH group acts as the directing agent and stabilize the charged intermediate. So this is a clean bronzic acid catalyzed reaction. Let's use this. Here, for different series of acids, different pKa value, and we realize that the deuteration rate constant is essentially in the arena dependent, is essentially the same for all these acids, homogeneous acids. It is related to the concentration of the hydronium ion in the solution. But if we take the torsolic acid and kind of put that onto the surface, I believe 15, the reaction rate increase. Catalysis at the interface are different in thermodynamics. What is more exciting is the following. If we now take here this ruthenium surfaces, and dissociation hydrogen undergo incipient ionization, and let's do the deuteration on the transition metal surface with hydrogen. We saw a change in the rate by 5 orders of magnitude. This is a clear evidence that this is the proton chemistry interfacial proton has formed, and it's going to attack a specific position in the phenol and undergo deuteration. We can then compare the second order rate constant for homogeneous versus the heterogeneous surface, and we could then understand that it is not only about the formation of the product, but it is the fact that reaction happen at the interface where you have the electrical double layer, where you have the charge, net charge density polarizing and stabilizing the transition state, that you get a remarkable turnover rate. Here, interfacial proton, how do they form? What exactly is their acidity? We wanted to speak the language by connecting here the liquid phase chemistry acidity of the proton to what we have known before, which is the deprotonation energy in the vapor phase. So these are gas-solid interface. The acidity of the proton is given by the deprotonation energy. In the liquid interface, we take here a hydrogen atom to evolve here a hydronium ion, and we compare this with the language of how we define here the acid dissociation constant at the pKa that describes here the dissociation of the hydrogen away from the metal side. This is the conjugate base. In order to form a hydronium ion, this part is given by the delta G for that step. Let's just probe and see what that is. So go here to define the delta G of liquid and solid interface. Do not worry where I take this part or how we go, because this is delta G is a state function. As long as I could zoom from one point and stop in another point, we are okay. It is a state function. So with here, allow me to just convert this kind of drawing a little bit, still the same thing on the gas-solid interface, liquid-solid interface. Let's just project that and connect our 3D thermochemical cycle. It is a fictitious part, but it allows us to decouple and analyze the delta G, the acid dissociation constant, by this framework as a theoretical value to explain what exactly is the acidity of the hydrogen on the transition metal surface. Turns out that there are a few key points. We have a property of hydrogen ionization and solvation property. The two key points here is the binding energy of the hydrogen, because you pull the hydrogen away on the surfaces, as well as the work function that require here to put the electron back to the electron back. Taking this part, we can then check here the periodic trend of different transition matter and their delta G. Delta G is related to their acidity, and the main component here is the work function that stands much more sensitively than the other compound. Here is the pKa value of different homogeneous water, phenol, acetic acid, and hydronium ion. Of course, they don't depend on the work function. Next, we overlay this number delta G related, back calculate the pKa and plot over here. One could see that the uncovered acidity for one hydrogen on the metal-water interface is related and a single value function for the work function of the metal. We also want to mention here that, of course, the co-adsorbate identity. For this case, we could have phenoxy species that come next to the hydronium ion, is able to influence and affect the work function, and therefore can shift this plot a little bit up or down in this part. The other point we want to mention is that this pKa of this value indicates that hydrogen is a weak acid. If we dissociate it on transition metal surface, we have hydrogen atom, we can also have hydronium ion, and we actually need both. You cannot have always proton attack, and attack to complete a chemical reaction. You must need hydrogen and atom balance with the hydronium ion, and these two chemistry kind of acting together to enable a complete turnover. So what we visualize here is the following. Activation of the hydrogen ionization to make here the interfacial proton, and then this proton is going to attract the phenol species in order, actually the phenol species that present in the electrical double layer, that is much more effective than the homogeneous acid because there is a net charge density happen. Here, formation of interfacial proton, and secondly, you have here a highly charged transition state that is stabilized by the matter, as also demonstrated earlier today by Matt Newrock in his earlier talk in a similar system in the phenol hydrogenation work. So let us now go here to look at how both hydrogen atom and hydronium ion can do here little dance step in order to enable the hydrodeoxygenation reaction that is much more effectively in water-ruthenium interface compared to the vapor ruthenium here. Lower activation barrier, higher rate when we scale everything and refer back to the same chemical potential of the substrate and hydrogen, and also higher than the cyclohexane ruthenium. How and why protic solvent could participate in this reaction? So let's look at it one by one. As I mentioned, this is not just one single step, everything is okay, there's nice correlation. These are multiple complex catalytic sequence involve multiple hydrogen attack. First of all, we take here 2-methoxyphenol. It absorbs on ruthenium metal surface in a way that is interacts strongly with the ruthenium ensemble through the aromatic ring. Here, there are 3 ruthenium carbon bond that is nicely laid out over here. Hydrogen is activated, and now there is 1 hydrogen attack. This is the first hydrogen attack to recover the dehydroxylated species. Next part, there is also a keto-enol isomerization. These are the charts that related to forming a more polar adsorbed surface species, and this part over here, and it turned out that this part is going to ring saturation. This is not the main point of what we want to do. These are sign reaction that this part here, hydrogenation of the aromatic ring go with this particular chemistry. And what we are looking at here is the desired carbon-oxygen bond scission that go from this part, and we need another hydrogen attack. We measure here the rate equation, and the rate equation has a meaning. The CO1 scission rate is related to the most abundant serving intermediate, and we know based on the kinetic evidence that we need 2 hydrogen attached. 1, and we need 1 more before we can get to the CO scission, and the CO1 scission, and divided by the most abundant serving intermediate. So we have 1 hydrogen attack that disrupt the aromaticity, weaken this interaction. We need the second hydrogen attack before we can climb the big barrier for CO scission. As we have measured here by the experiment, and we want to check here with what we do. So the free energy landscape, the enthalpy come as the following. Start from most abundant surface intermediate, form here the reference, this is the reference state, 1 hydrogen attack, followed by second hydrogen attack. At this point, it is ready now to cleave the CO bond. And noting that all these parts here are quasi-equilibrated because you haven't climbed the difficult transition state. So we can actually probe and confirm that we need 2 hydrogen based on these isotopic labeling study. This is the reactant, it can go back and forth. If it go back and forth many times, if you bring a D, you could check here, we detect up to 3D reactant. Cannot have 4, because 4 is the cleavage of the CO bond. So after you do that, we can also confirm where exactly is the hydrogen attack occur. We could check here by the NMR, and that point is disappearance for this peak, indicating that that hydrogen is attack. This hydrogen attack is on the metal C5 position because this peak decreased, and this is where the reactant and adsorption species that roll back and forth, and before they climb the larger step. Finally, we go on to the point, I just want to kind of remind us that they are keto-enol-tautomerization, and don't worry, they are quasi-equilibrium, they're swimming on the surface at the equal chemical level. And this one go to the ring saturation, this one go to the CO scission and confirmed by the reactive calculation. So next step here is about this part CO scission, then we go to hydrogen attack at this point, let's see what happens. Now, the precursor here is one hydrogen added into the wire core species is ready to now go on to form the transition state. To analyze this situation, we see what is the effect of water. One water molecule here participates and assists with the transfer of this hydrogen, either forming a bronzic acid hydronium ion and promote this cleavage over there. And this is where this part needs to cleave. At the transition state here, hydrogen, a proton is fully formed, CO cleavage is on the early side, and most importantly, the metal center acts as the balance of the charge to stabilize this highly charged transition state. Because of that, the barrier required to cleave this bond is 60 kilojoule per mole. Without that, the barrier is above 110 kilojoule per mole. Clearly, this is more the faster pathway. So, the hydrodeoxygenated chemistry is actually quite complicated. It requires multiple hydrogen and proton involvement. How they involve, what position that they involve to attack this ring really shape the entire free energy landscape, and this side here, the reactivity. This requires here a small jump. First hydrogen attack, second hydrogen attack, before you can just cleave the CO bond. You cannot just jump. You need one step, two steps, you need proton involvement, you need hydrogen attack to weaken the aromaticity. That gives you the entire landscape over here. And by manipulating how we stabilize the charge, not only the proton, we also need here the double layer that have a net charge polarization. In order to stabilize this highly charged transition state, we also need one water molecule here to assist with the moving of the proton and to cleave on the CH bond and go from that. So with that, let us now go on. Falling down from the transition state, and methanol, CO bond cleave, and methanol is leaving accordingly, and that completes the catalytic cycle. So basically, we require here one hydrogen attack, two hydrogen attack, followed by a CO bond scission, and next we can go on to complete this cycle that is competing with the ring saturation catalysis. So with here, and come back to the end of my talk. Activation of hydrogen on transition matter leads to multiple charges. The electronic charges of the hydrogen depend on, of course, the d electron of the matter, and depend on how the donation into the hydrogen atom, and it depends on whether we form a hydride proton pair, and both has their own unique catalytic role in the reaction. And in the presence of the solvent, water could help, a protic solvent could help with the formation of the interfacial proton. And such interfacial proton will carry out chemistry that is non-attainable in a normal vapor transition method interface. And we show here the free energy landscape had changed by using a simple carbonyl hydrogenation reaction because it's only two dance steps. You go with the left foot forward, CH bond formation, you go for the right foot forward to go OH bond formation. End result is the same. Details are not the same. Rate is not the same. Rate equation are of course not the same. And we can tune this by having a hydrogen atom, having a local proton hydride without the solvent, or we immerse everything into the liquid and ask the interfacial hydronium ion to do the chemistry. And we also have here the electrical double layer that I have not touched on, but it gives an indication. It's not only about the proton. It is about the matter that acting to stabilize the charge transition state that give you the reactivity several order of magnitude higher than what we would expect compared to the vapor phase. And because of this complication, the acidity of the hydrogen atom on the transition metal surface depend on the hydrogen property, binding energy balance with the work function on the transition metal. And of course, this part here depend on the solvent identity, whether you have a polar protic solvent, polar aprotic solvent, and that play this part of the chemistry, and that leads us to different reactivity track. Either the rate increased by proton affinity for the aldehyde hydrogenation in the protic solvent, or the rate here increased by hydride affinity for the aldehyde hydrogenation on the hydride proton pair. And it is because hydrogen is so simple. It has different kind of charges, and we can play around with this all the time with different chemistry. And this is what is very, of course, it's very useful to undergo reductive chemistry and cleave CO bond. And we could actually come back to explain the reactivity, to rationalize how we wanted to behave in a simple way by breaking this down one by one. So with that, I would like to next thank the individual who are together with me, my group, and our collaborator in this journey to understand here a very simple chemistry, how we attack the different molecules using only one hydrogen, ask the hydrogen to do some dance in the free energy dance stage. I thank here my group, in particular, individual, talented individual who have done this work, Hai Ting Kai, Alista Hensley, Junnan Sangwang, and Jen Wei Wu, our collaborator, John Sabina Allen, Robert Morris, and Mano Mamaskakis, and collaborator in DuPont, Surab Sanguta, and Joe Ritter. Thank you so much for the invitation.
What a lively presentation. Any questions?
Nice work. I was wondering what happens to rates of carbonyl reduction as you change the pH of the solution?
I see. It depends on when we change the pH. That depends on how you change the pH. Right? If you provide here different ion, then we need to deal with the non-ideal chemistry, and we need to account for the presence of different. For example, a while ago we have changed it by doping with some sodium, for example, sodium acetate. And this is, we need to be very careful about this because the acetate would absorb on the surface. There are multiple events that could happen. And it is rather complex to be able to decouple the fact how you change the pH. You are changing different ionic strength of your, and you need to know all those constants to account and analyze your rate equation. We do that, and the multiple events happen. There is no, we are not able to clearly only change the pH without changing or without accounting for all the non-ideal situation. And we are still thinking about how to deal with that. So you could get multiple answers.
Okay, any more questions?
Cathy, great talk. As usual, I'm confused. No, as usual with your talk, I'm generally confused. I listened to the talk of one of Enrique's students earlier this week when he'd done hydrogen deuterium exchange on platinum, I think, it was not ruthenium, and he was emphasizing water doesn't matter. Hold. Let me. My confusion is not at an end, and you really need to help me. Second question is, then I meet Roger Russo, and Roger Russo has beaten in my head this, that there is no hydronium ion with a bond to a metal surface, because as soon as it's there, the electron pool will annihilate that proton. So hydronium ions are in the Helmholtz layer and they're out. So it's an outer sphere proton transfer in this one. I think to adhere to the latter rather to the former. So help me, where is your position and how can you clarify this with the mechanism that you have shown?
Well, first, I'm not here to answer question for others in the talk.
No, that's not what I have. I only wanted to help you in my confusion.
Okay. Secondly, I think I was not very explicitly mentioned that when we define or do our exercise on the acidity of this hydrogen, the delta G is related to taking the hydronium ion far away from the matter to the mild liquid phase. There is a difference when you do the chemistry with hydronium ion in the homogeneous phase without any landing site, or the chemistry in the double layer where you have here the net charge situation. I think that Matt has explained this one earlier today, that you need this. You need the matter to anchor and stabilize the charge transition state, right? And what happened to Roger Russo?
No, Roger only told me that there is no proton at the surface, with a bond at the surface. So, and I think you explained this in part in this. Okay.
Well, it seems that I have some time, right? I think my clock is okay. Then I can provide a more.
Matt wanted to comment.
Oh, you
on
want
this
to
one.
help me too? That's very good.
I think Cathy commented on, in your case as well as in here, if you dump electrons into the metal, you got a proton, and but that proton is near the surface. It's not. It's
no, but it's in the Helmholtz layer. It's not at the surface. It's not above.
it can be in a variety of positions. It's most likely going to be above where it's interacting with the oxygens.
For me, the question is this then not are we not
talking here actually about the redox potential that we're having on an open circuit potential? Are we now? Can we use an open circuit potential in the same way as we can talk about an acid strength let's say in a non-conductor?
Okay, now I think you want to review it. Okay. No, but maybe let me make a confrontational statement if everyone is here. So, since you confronted me first, right? So, what we are trying to do is to breaking down the acidity in a simplistic sense and communicate to see how the trend changes in the transition method, right? The other thing is the open circuit potential, the definition, because this is a thermodynamic property. Right? And there is one thing that the field are still unclear because nobody want to talk, nobody can come to the conclusion or not very clear in the textbook, is that when you generate this hydronium ion, where do you put the electron? The standard state is in the vacuum. Okay, I can bring you a textbook to the standard state when you make the hydronium ion, the electron is referred to in the vacuum. This will take us multiple textbooks to come to this point. Well, so since everyone can speak and listen to this, so we can have a good discussion.
Good.
And that is not directly related to open circuit potential. That is one point.
It doesn't go into the vacuum, but this is a different.
But the definition is yes, and the reference state, the electron, because nobody said where the electron is putting. And the other thing I want to mention is that I go quite fast, is that we do torsidic acid in the homogeneous reaction, and that rate is consistent with all the rate evaluated when we divided the rate by hydronium ion, accounting for the acid dissociation constant. If you put that acid totally acid all the way on the surface, in the amylase surface, then the rate is an order of magnitude higher. So it indicates that the solid surface actually has a way to stabilize the transition state. And this is something we haven't, we are studying that, and we study how the reaction happens at the interface. The same thing, the totally acid, the homogeneous and on the surface. The one on the surface has higher rate, because the surface actually play a role. It's not about the concentration of hydrogen ion or the local, it is about the charge. That's why I emphasize that it's not only about this one to form here, it's about the reaction happen inside the double layer that make it happen. I know it's difficult to quantify the charge, and
I agree with Cathy, I agree with you completely. I think the surface does have because you have more probability of quantity also to displace the electrons to stabilize that on the surface. I agree completely on everything. The only thing is if you look at the role of particular
when you want to close this thermodynamic cycle for the proton, the redox pair of a proton and hydronium ion, you do of course have to consider your electron affinity of your metal, and therefore you do change your band structure and your local Fermi level, because you fix as you put it in water, you fix by your pH, you fix actually the Fermi level in the metal. And that is that equilibration between your redox pair and your metal that defines the new state of the Fermi level, or the Fermi level against the vacuum level in the metal in water. But that's now a more subtle discussion that goes way beyond that.
Well, looks like you guys will have a lot
Minus
of
60.
conversation. Okay. Well, I think we'll have to keep on time. Let's thank Cathy again for the very valuable presentation.